Okay, picture this. You've written some code, you hit run, and you're just waiting, staring at that spinner,
Oh, yeah.
maybe that sad face gif from the article we looked at, feeling like maybe it's faster to solve this by hand.
Mm.
It's that universal, soul-crushing frustration of slow code.
It really is. And look, everyone hits this wall. When you start coding, the main goal is just making it work, right? Which is absolutely the priority.
Totally.
But then you build something and it just crawls. That script that takes hours or the app that just freezes up.
Exactly. And that's what this deep dive is all about. We're digging into the insights from this article, why your code is slow, common performance mistakes beginners make. Our mission, to kind of unpack these key pitfalls that just tank code speed and, maybe more importantly, figure out how we actually fix them.
Yeah, and the author kicks it off with this great, super relatable story. They wrote a script, took 3 hours to run,
Wow.
got it down to 10 seconds with just one line change.
One line.
Yeah.
That's incredible. It really shows the power of understanding these bottlenecks.
Absolutely. It's not magic. It's just knowing where to look.
So the plan is we'll walk through 7 common mistakes the article highlights, and then we'll shift gears and look at how professional developers approach writing fast code, sort of their mindset.
Sounds like a solid plan. Let's get into it.
Okay, diving right in. Mistake number 1. It seems so innocent at first, doesn't it? It's logging everything in production without really realizing the cost.
This is so, so common because when you're developing, you sprinkle print statements everywhere or you turn on really verbose debug logging.
Right, just to see what's happening.
Exactly. Log every function call, input, output, maybe even the whole request body or database query. It feels helpful, like leaving breadcrumbs.
But why is that such a big deal once your code is live? Isn't seeing what's happening still good?
Well, the issue is logging isn't free. It actually takes processing time for every single log message. And often, especially simple logging, it's synchronous, which means your main code literally stops executing and waits for that message to be written to disk or wherever.
Oh, okay. I didn't think about the stopping part.
Yeah. Imagine, like the article says, a print statement inside a loop that runs, say, 10,000 times.
Yeah.
Or 1,000,000.
Right.
That tiny pause multiplied over and over, it adds up massively. It becomes a real bottleneck.
Plus, I guess it creates just a ton of noise in the logs, right? Makes it hard to find the important stuff.
Yeah.
But it eats disk space.
Exactly. All of the above. So the fixes are pretty straightforward, thankfully. First, just be more strategic about what you log in production.
Okay.
The article contrasts bad logging, like logging every little micro step, with better logging, which focuses on significant events. Think transaction start, success, failure, things you actually need for monitoring or critical debugging.
Log smarter, not harder. Got it. What else?
Second, you absolutely need to manage your logging levels. Debug logs, great for development, but they have to be turned off in production.
How do you do that reliably?
Well, most languages and logging libraries let you set a minimum level. Like in Python, logging.basicconfig, level logging.info. This tells the system, ignore anything less important than info, so all those login.debug calls just do nothing.
So the code for the debug message is still there, maybe, but it's effectively switched off unless you change that setting.
Precisely. It's safe and configurable, and, for really high-performance systems where even writing INFO logs synchronously could be an issue.
There's another level.
Yeah, you might need to consider asynchronous logging. Python's queue handler is a good example. It basically puts the log message onto a queue really fast, and then a separate background thread handles the actual slow part of writing it out. Your main code doesn't wait.
Okay. Pushing the slow work off to the side. That makes a lot of sense. So the takeaway here is logging costs real resources, especially in production. Be intentional, control your levels, maybe go async if you need top speed.
Absolutely. Logging is I/O input-output,
Yeah.
and I/O is almost always slower than just crunching numbers in the CPU.
Good point. Okay, moving from logging, mistake number 2 seems almost too simple. Using the wrong loops when there are faster alternative.
Yeah, for loops. They're fundamental, right? Often the first loop you learn. They feel very intuitive, very controllable. So it's natural to just default to using a for loop for, well, everything.
And what's the problem with that? If it works, it works.
Well, while for loops are fine for many things in certain languages, and Python is a really big example here, a simple for loop, especially if you're doing things like building up a new list inside it, can be noticeably slower than using built-in constructs optimized for that task.
Like the article's example of squaring numbers. Building a new list with .append. inside the loop.
Exactly that one. New list.append, item 2, over and over. That pattern involves manual iteration in Python code, plus repeated calls to the .append method, which has overhead. It dynamically grows the list.
Okay, maybe not noticeable for 10 items, but for 10 million.
For 10 million, it becomes the bottleneck, definitely.
So what's the faster way then?
You embrace the language features designed for these kinds of transformations. In Python, the classic answer is list comprehensions.
Ah, the ones in square brackets.
Yeah. The article shows squared equals num2 for num in numbers. It's cleaner, it's shorter, and critically for this type of operation, it's much, much faster.
Okay, it looks nicer, I agree. But why is it faster? Is it just like syntactic sugar?
Ah, good question. No, it's more than that. Often, Python can optimize list comprehensions to run parts of the loop in highly optimized C code under the hood.
Oh, interesting.
This avoids a lot of the overhead of pure Python function calls, like calling .append repeatedly. Plus, Python can often figure out the final size of the list beforehand and allocate the memory all at once, which is way more efficient than resizing the list bit by bit.
Gotcha. So it's tapping into a faster, lower-level implementation.
You're
Less
right.
overhead, better memory allocation.
Exactly. It's faster, usually more readable for these simple transformations, and actually less prone to silly mistakes like off-by-one errors you might get with manual indexing.
But the article does mention standard for loops still have their place, right?
No, absolutely. If the logic inside your loop is genuinely complex, multiple steps, conditional branches,
Yeah.
or if you specifically need to modify the list you're iterating over in place.
Which can be tricky.
Yeah, or if the loop involves side effects like writing to a file for each item or making a network call, then a traditional for loop is often clearer and the right tool for the job.
So the key insight here, don't just default to the first loop structure you think of. If there's a specialized optimized tool like a list comprehension for your task, use that.
Right. Use the right tool for the job, even when iterating.
Okay, third on our list. This one is a real classic performance killer. Writing database queries inside loops.
Ugh, yes. The N+1 problem. This one is painful because it often works fine during development with just a little test data.
Right, it feels natural. You have a list of things, say user IDs, and for each ID, you need to fetch that user's data from the database. So you just put the database call inside the loop.
Like for userit in userids.userit, logical sensors.
He's like, what's so bad about that?
Every single call inside that loop that goes out to the database costs a lot. There's network latency sending the query over.
Okay.
Then there's processing overhead on the database server itself to handle that query. And then network latency again to send the results back. If your loop runs, say, 1,000 times, you're making 1,000 separate expensive round trips to your database.
Instead of potentially just one.
Exactly. That's the N+1 problem. You fetch N items, but it takes N database queries plus the initial one to get the list. Performance just falls off a cliff as N gets bigger.
Okay, that makes sense. So the fix is obviously don't do that.
Pretty much. The fix is to use bulk queries. Instead of N separate queries for N items, you want to make one query that fetches all the data you need for all those items in a single shot.
How does that look?
The article shows the basic idea. Select from users where it in. You collect all the user IDs you need first, then you send them all to the database in one query using that in clause.
Okay, get the list of IDs, build one query with where it in, ID 1, ID 2, ID 3, and get all the user data back at once.
Precisely. This massively cuts down on the network back and forth, drastically reduces the load on your database, and makes your whole application feel much snappier and more scalable.
And the article mentioned ORMs often help with this, object relational mappers.
Yes, absolutely. Most good ORMs like SQLAlchemy or Django in Python, or maybe SQLize in JavaScript, have built-in ways to handle this. They often call it batch fetching or eager loading.
So the ORM figures out how to do the efficient query.
Often, yes. If you use the right methods, like maybe filter user.id.users and write.id.all and SQLAlchemy, it translates that into the efficient single select in query behind the scenes. You just need to know how to ask the ORM to do it.
So the big takeaway, avoid the N+1 database query pattern like the plague. Fetch data in bulk whenever you can.
Batching is definitely your friend when talking to databases.
All right, moving on. Mistake number 4. This takes us into a slightly different realm, something maybe fewer developers think about day to day, not knowing your hardware's dirty secrets.
Yeah, this is where performance optimization can start to feel a bit like black magic if you haven't dug into the fundamentals. Your code isn't just abstract logic. It runs on real physical hardware. CPUs, memory, caches. the OS, and they all have their quirks.
The article breaks this down into a few specific issues. First, the CPU's crystal ball is broken, which is about memory prefetching.
Right. So CPUs are incredibly fast, way faster than main memory RAM. A lot of the time, the CPU is actually just sitting there waiting for data to arrive from RAM.
Okay.
To try and hide this delay, CPUs have a trick called prefetching. They try to predict what data your code will need next, and they fetch it from RAM into their own super-fast local cache before your code actually asks for it.
So it's like the CPU is trying to read ahead in the instruction book.
Exactly. And it works brilliantly if your code is accessing memory sequentially, like iterating through a normal array where elements are stored one after the other. The CPU can easily guess, okay, they just asked for address 100, they'll probably want 104 next.
Makes sense. But what breaks it?
Random access patterns. If your code is jumping all over memory unpredictably, maybe traversing a linked list where each node could be anywhere, or doing lookups in a hash table that's causing lots of collisions and probing different memory spots.
The CPU can't predict the next address.
Nope. Its crystal ball is broken, it guesses wrong, the data isn't in the cache when needed, and boom, the CPU has to stall and wait for that slow trip to RAM. The article used the analogy of trying to use Google Maps with spotty internet. It keeps failing to load the next bit.
And this is especially bad in hot loops, right? The code that runs millions of times.
Absolutely critical there. Even small stalls multiply incredibly fast in hot loops. So the fix, generally, is to favor data structures that keep data contiguous in memory.
Like arrays.
Yes, standard arrays, or things like NumPy arrays in Python. They store data in nice, neat blocks, sequential in memory. When you loop through them, the CPU's prefetcher is happy. It works perfectly, keeping the cache full of relevant data.
Okay, keep data close together in memory. Got it. What's the second hardware secret? The invisible tax of memory pages TLB thrashing. This sounds technical.
It is a bit, but the concept is important. The operating system doesn't manage memory byte by byte. It divides it into fixed-size chunks, usually 4 kilobytes, called pages.
Okay.
When your code uses a memory address, the CPU needs to translate that virtual address your code sees into the actual physical location in RAM. To speed this up, it uses another special cache called the TLB Translation Lookaside Buffer. It's like a small, super-fast cheat sheet for recently used page translations.
A speed dial list for memory pages.
Good analogy. Now, what happens if your code is accessing data that's spread across tons of different, unrelated memory pages? Like the article's example, iterating through a massive list but accessing elements at completely random indexes.
You keep needing translations for pages that aren't on the cheat sheet.
Exactly. You get lots of TLE misses. For each miss, the CPU has to stop, go through a slower process involving the OS to find the translation, and put it in the TLB. Each miss costs cycles.
And the article said this can waste millions of cycles if it happens enough.
Oh yeah, if you're doing millions of random memory accesses that hit new pages constantly, those small cycle costs add up to a significant invisible tax on your performance. TLB thrashing.
How do you fight that?
One way is to try and process data in smaller chunks that are more likely to fit within fewer pages, improving locality. Another, on systems that support it, is to use huge pages, maybe 2 megabytes instead of 4 kilobytes. Fewer, bigger pages mean fewer translations needed overall, reducing TLB pressure.
Okay, third hardware issue. Your code is a tourist in the wrong CPU neighborhood, Nume. What's Nume?
This mainly applies to bigger servers, the kind with multiple physical CPU sockets. NUME stands for non-uniform memory access.
Non-uniform, meaning access times aren't the same.
Exactly. On these multi-socket systems, each CPU socket typically has its own directly attached RAM. Accessing that local RAM is fast, but accessing RAM that's physically attached to a different CPU socket is significantly slower because the request has to travel across an interconnect between the sockets.
Ah, the article's analogy. Ordering Uber Eats from across town instead of next door.
Perfect analogy. So imagine you have a multi-process application. If a process running on CPU 0 is constantly trying to read or write data that happens to be stored in the RAM attached to CPU 1, it's always taking that slower cross-socket path.
Even though there's plenty of CPU power, the memory access becomes the bottleneck. The Python multiprocessing example accessing a remote array showed this.
Precisely. The fix here is to be NUMEM aware. You can use operating system tools, like numac Tula on Linux, to explicitly pin a process to run only on cores within a specific NUMEM node, CPU socket, and allocate its memory locally on that node, or use libraries designed to handle this automatically.
Okay, and the final hardware quirk. The CPU is a drama queen speculative execution.
Haha, yeah. Modern CPUs are incredibly aggressive about trying to guess the future. When they hit a branch in the code, like an if statement, they often don't wait to see if the condition is true or false.
They just guess.
They make an educated guess based on past behavior, and they start executing instructions down the path they think the code will take. This is speculative execution. If they guess right, great, they've saved time.
But if they guess wrong?
Drama. It's called a branch misprediction. The CPU has to throw away all the work it just did speculatively down the wrong path, reset its state, and then start executing down the correct path. This rollback wastes valuable CPU cycles.
And this happens a lot with unpredictable if conditions inside hot loops.
Exactly. If you have an if statement in a tight loop and the condition is basically random, sometimes true, sometimes false, no clear pattern, the CPU's branch predictor keeps guessing wrong, and you pay the misprediction penalty over and over.
Like betting on coin flips inside your loop and losing half the time.
Pretty much. The fix. Try to make your branches more predictable if you can. The article suggests sorting your data first. If you process all the items where the condition is true, then process all the items where it's false, the CPU sees long runs of the same outcome and predicts correctly almost every time.
Wow. It's a lot of low-level stuff affecting high-level code. How do you even diagnose these specific things?
Yeah, it's deep. But the article's key advice here is profile, don't guess, use tools that can actually measure these hardware-level events. Linux perf is a powerhouse for this. The example perf.stat cache misses pagefaults.yourcode directly measures cache misses and page faults, which can point towards prefetching issues or TLB thrashing.
So the big takeaway from all this hardware stuff, your code isn't running in a void. Memory layout, access patterns, even data ordering matter immensely because of how CPUs, caches, and memory actually work. You have to profile to see these effects.
Assume nothing about the hardware, measure everything, and try to work with its strengths, not against them.
Okay, moving away from the deep hardware secrets, let's tackle mistake number 5. Another memory-related one, memory fragmentation.
Right, this is a bit more subtle. It's that weird situation where your system monitor says you have plenty of free RAM available overall, maybe gigabytes free, but your application suddenly crashes with an out-of-memory error when it tries to allocate a reasonably large block.
Because the free memory is all broken up into tiny pieces.
Exactly. It's the Swiss cheese memory effect the article describes. Imagine your program allocates a block, then another block of a different size frees the first one, allocates a third smaller block. Over time, the memory manager ends up with lots of small unused gaps scattered between the blocks that are still actively in use.
Like holes in Swiss cheese.
Precisely. So you might have, say, 1 gigabyte of total free memory, but if it's fragmented into thousands of tiny 1 kilobyte chunks, and you try to allocate a single 2 kilobyte block, you can't. There's no single contiguous free block large enough, even though the total free space is huge. The C++ server example allocating random buffer sizes really illustrates this.
So you run out of usable large blocks, even with free RAM. The fix for this, especially in languages like C++F, is something called a memory pool. Yes, that's a common strategy. Instead of asking the operating system's memory manager for lots of differently sized blocks frequently, you allocate one big chunk of memory up front the pool. Then your application manages allocations within that pool, usually by dividing it into fixed-size blocks that you hand out and reclaim.
And because the blocks are fixed size, you don't create those random gaps.
Right. It prevents fragmentation within that managed pool, ensuring you can reliably allocate blocks of that specific size.
Okay, that covers heap fragmentation. The article also brings up the autoboxing trap. This sounds more relevant for languages like Java or C#, maybe. Definitely. So languages like Java and C# distinguish between primitive types, like int, float, Boolean simple values, and their corresponding object wrapper types, integer, float, Boolean. Autoboxing is a convenience feature where the language automatically converts a primitive value into its object wrapper when needed, like putting an int into a collection that expects integer objects.
Okay, so if I have a Java arrayless integer, and I just try to add the number 5, an int, the compiler silently converts that int into an integer object behind the scenes.
Exactly. It boxes the primitive inside an integer object on the heap. And the reverse, unboxing, also happens automatically. It's convenient, makes code cleaner sometimes. But doing this repeatedly, especially inside tight loops or performance-critical code, is surprisingly costly for a few reasons.
Okay, what are they?
First, memory overhead. Each integer object takes up more memory than a raw int because objects have headers and other baggage. Second, garbage collection pressure. These temporary wrapper objects are created on the heap, used briefly, and then become garbage that the GC has to clean up later, which can cause pauses.
Right. And third, cache inefficiency. A bunch of integer objects in an array list might be scattered around in memory on the heap, whereas an array of primitive ints would be packed tightly together, which is much friendlier for the CPU cache.
Wow. So a seemingly harmless convenience feature cascades into memory bloat, GC pressure, and poor cache performance, especially in loops.
It really can, yes.
Right.
The fix is to be aware of it, and when performance matters, try to use collections specifically designed to hold primitives directly. The article mentions Java libraries like Eclipse collections, which have things like int lists that store raw ints.
And for C#, using structs or spanT.
Exactly. C# structs are value types, so they often live on the stack or directly within containing objects, avoiding heap allocation and GC pressure entirely. And spanT is a powerful feature for working efficiently with contiguous blocks of memory, like arrays or parts of arrays, without any allocations or copying. So the takeaway for fragmentation and autoboxing. Understand how your language manages memory, especially the difference between primitives value types and objects reference types. Use specialized primitive collections or features like spant when dealing with lots of primitive data in performance-sensitive code.
Yep. Think about the underlying memory layout and the cost of creating objects.
All right, mistake number 6 is titled the cache catch. This brings us back to hardware caches again, but specifically focusing on how you access data in multidimensional arrays.
This is one of those classic computer science performance lessons that really surprises people. You have a 2D array, like a grid or a matrix. Intuitively, you'd think iterating through it row by row should be about the same speed as iterating column by column.
Yeah.
Right?
Seems logical. You're accessing the same elements, just in a different order.
But it's often drastically different because of how that 2D array is actually laid out in the computer's linear memory.
Memory is just one long line.
Exactly. And most common languages like C, C++, Java, and Python with NumPy's default use what's called row major order. This means all the elements of the first row are stored contiguously, then all the elements of the second row, and so on.
Okay, so row 0, call 0, row 0, call 1, row 0, call 2, then row 1, call 0, row 1, call 1, all in a line.
Right. So if you write your loops to iterate row by row, meaning the innermost loop changes the column index, the next element you access is usually right next to the previous one in memory.
And the CPU prefetcher loves that.
Loves it. When the CPU loads the current element into its cache, it almost certainly brings in the next few elements of that row too, because they're physically adjacent and likely fall on the same cache line, the chunk of memory the CPU fetches at once. Result, cache hit, super fast access.
Okay. But what if I iterate column by column on that same row major array? So the inner loop changes the row index.
Then each step in your inner loop jumps over a whole row's worth of data in memory to get to the element in the next row, but the same column. That element is almost guaranteed not to be adjacent to the previous one in memory.
So it's probably not on the same cache line.
Very unlikely, which means for almost every element you access in that inner loop, the CPU has to stall, go fetch a completely new cache line from main memory. Cache miss after cache miss.
And that's slow. How slow?
The Article C example using a PUM24 by 1024 matrix showed something like 5 milliseconds for the cache-friendly row major access versus 50 milliseconds for the cache-unfriendly column major access. A 10x slowdown, just from changing the loop order.
Wow, 10x, just for accessing the same data differently. And then there's the language gaslighting twist.
Yeah. The plot twist is that not all languages default to row major. C, C++, Uvo, Java, Python, NumPy usually do. But Fortran, MATLAB, R, Julia, they typically default to column major order.
Oh, so in Fortran, it's the columns that are stored contiguously.
Exactly. So in Fortran or MATLAB, iterating column by column is fast and row by row is slow. If you take C-style row major loops and run them in Fortran or vice versa, you're fighting the language's natural memory layout, and you'll pay that cache penalty.
So you really need to know your language's default layout or library's layout, like NumPy's order C versus order F, and match your loop access pattern to it.
That's the core fix. Match your loops to the memory layout. Or, if you can't change the loops, sometimes you might need to explicitly tell your library to store the data in the other order, like order F for Fortran column major order in NumPy, or even transpose the data first.
What about arrays with more dimensions, like 3D or 4D?
It gets even more critical. The multidimensional illusion part of the article explains it. Think of a 3D array in C, row major. It's essentially an array of 2D arrays, which are arrays of 1D arrays. Each dimension adds another layer of potential jumps in memory. The key is that only the last index, the innermost dimension, corresponds to contiguous memory access in row major. If your innermost loop iterates over one of the outer dimensions, you're constantly jumping between these large 2D or 1D slices, completely destroying cache locality.
And the article mentioned this could lead to, like, a 100x slowdown.
Potentially, yes. The C3D array example showed how simply reordering the IJK loops to ensure the innermost loop varied the last index made it dramatically faster than looping over the first index innermost.
That's incredible. 100x.
It really highlights how vital cache-aware programming is for scientific computing, image processing, anything dealing with large n-dimensional arrays. The article even briefly touches on advanced techniques like tiling, processing small blocks that fit in cache, or using structure of arrays instead of array of structures, AOS, for better vectorization, SIMD, which are like the nuclear options built on these cache principles.
So the key takeaway for cache access: the order you traverse multidimensional data is critically important due to CPU caches. Know your memory layout, row major versus column major, and make sure your innermost loop iterates along the contiguous dimension.
Work with the cache lines, not against them. It makes a huge difference.
Okay, we're on to the last of the 7 common mistakes: the copy-paste trap. This sounds less about algorithms and more about accidental side effects.
It is, often. It's about situations where your code silently creates copies of data when you might not expect or intend it to, leading to unexpected memory consumption and slowdowns.
How does this happen accidentally? Like, what's the first problem?
Problem one the article highlights is ghost copies and harmless operations. A super common example, especially in Python, is slicing a standard list. When you do mylist start.end, Python doesn't just give you a view into the original list, it actually creates a brand new list containing copies of the elements from that slice.
Wait, really? So if I have a list with 1,000,000 items and I do small slice mylist 0.10, Python makes a completely new 10-element list.
Yes. It allocates new memory for those 10 elements and copies them over. Now, for 10 elements, that's trivial. But what if you slice a large chunk? Or what if you do mylist to seemingly get the whole list? That creates a full, potentially gigabyte-sized copy of the entire list.
Whoa! And if you did that inside a loop?
You could easily blow through your memory. It doubles memory usage instantly for a full slice. And repeated slicing of even moderate chunks in a loop generates tons of temporary objects and memory pressure.
The article contrasted this with NumPy arrays, right? Where
Yeah.
slicing usually gives a view.
Exactly. NumPy is designed for performance. When you slice a NumPy array, like my NumPy array start.end, by default you get a view. It's a new object that refers to the same underlying data as the original array, just potentially looking at a different part of it. No data is copied. Much faster, much more memory efficient.
So the fix is to use things that give you views or references.
Yes, whenever possible. Use NumPy views, or Python's built-in memory view objects, or features like lazy slicing in pandas like .iloc, or specific language things like JavaScript's typearray.subarray. Always ask yourself, do I really need a completely independent copy right now, or do I just need to access part of the original data?
Okay, problem 2 under copying: the hidden cost of functional code. This sounds slightly controversial. Functional programming is often praised.
And it often is, for clarity and avoiding side effects.
Yeah.
But the potential performance trap comes from chaining multiple operations like map, filter, slice on collections, especially in languages where these operations eagerly create new collections at each step. The JavaScript array example in the article is a good illustration.
So if I have my array.filter.
In many default implementations, filter runs first and creates a whole new temporary array containing only the filtered elements.
Okay.
Then map runs on that temporary array and creates another new temporary array with the mapped elements.
Right.
And then slice runs on that second temporary array to create the final resulting array.
So you've potentially created 2 large intermediate arrays that you didn't really need.
Exactly. You've iterated over the data multiple times and allocated memory multiple times. If your original array was large, this can be significantly slower and use much more memory than a single traditional loop that performs the filtering, mapping, and selection logic all in one pass, writing directly to the final result array.
Or using lazy evaluation, like generators.
Yes, generators are a great solution here. Things like Python's yield or JavaScript's function allow you to create pipelines that process items one by one on demand without ever building those large intermediate collections in memory. Much more efficient for chained operations on large data sets.
Okay. And the final copy trap. I'll just Modify copy mistake.
This is about making copies of complex objects, especially using deep copy functions, often inside loops. Imagine you have a big configuration object, maybe a deeply nested dictionary or a complex class instance, and you need to create slightly different versions of this config for, say, many different users.
Your first thought might be to just copy the whole thing and tweak it.
Right. And you might reach for something like Python's copy.deepcopy, which recursively copies everything, including all nested objects.
That's bad.
It's slow. Deep copying is significantly more expensive than a shallow copy, which just copies references to nested objects, or even better, constructing a new object. The article mentions deep copy can easily be 10x, maybe even 100x slower than alternative approaches. Doing that repeatedly inside a performance-critical loop is just burning CPU cycles unnecessarily.
So the fix is, don't use deep copy in hot loops. Use something else.
Pretty much. Favor patterns that avoid deep cloning in loops. Maybe use immutable data structures where you create new versions by merging the base data with the specific changes, rather than cloning and mutating. The Python example, baseconfig userparif value, shows creating a new dictionary by efficiently merging, which is way faster than deep copying the whole baseconfig first.
The overall takeaway for this copy-paste trap section: be really conscious of operations that might be copying data, especially large data or complex objects, and especially inside loops. Prefer views and references over copies, consider generators for functional chains, and avoid expensive deep copies in performance-critical paths. Profile your memory usage.
Assume things might be copying unless you know they aren't. Question everything.
Okay, we've made it through the 7 common pitfalls. That was a lot. Now let's flip the perspective. How do professional developers write faster code? It's not just about avoiding these mistakes, right? It seems like a different way of thinking.
It absolutely is. It's a mindset shift backed by specific practices. And the very first pillar, the foundation, is they profile their code instead of guessing.
Right. They don't just think, this card feels slow. They use tools to get actual data.
Exactly. Guessing where the bottleneck is one of the biggest time wasters in performance tuning. Pros use profilers tools like Python cprofile or perf on Linux, maybe line profiler for line-by-line timings, jprofiler for Java, valgrind for CC++, plus Grilda browsers, dev tools for web stuff. These tools tell you exactly where the code is spending its time, which functions are slow, which lines are hotspots, how much memory is being used where.
You can't fix what you can't measure.
That's the mantra. Measure first, then act.
Okay, which leads directly into the second pro tip. They avoid premature optimization.
Yes, the classic Donald Knuth quote. Premature optimization is the root of all evil. It means resist the urge to spend hours tweaking and micro-optimizing some clever bit of code before you know if it's actually part of the performance problem.
Like spending half a day shaving microseconds off a function that only runs once, when the real problem is a 5-second database query happening elsewhere.
Precisely. Get the code working correctly and clearly first. Then run the profiler. If the profiler points to a specific bottleneck, then you focus your optimization efforts only on that slow part. Trying to optimize everything from the get-go often leads to complex, hard-to-read code and wasted effort.
Make it work, then make the slow parts fast. Okay, point 3. They pick the right data structures.
This is absolutely huge and something that separates experienced developers. Beginners often just reach for the default collection type, maybe always using a list or an array. Pros understand that the choice of data structure can have a massive order of magnitude impact on performance depending on how you're using the data.
Like the classic example of looking something up in a list versus looking it up in a set or dictionary.
Exactly. Checking if an item exists in a standard list requires, in the worst case, looking at every single item. That's OAE, complexity slow for large lists. Checking if an item exists in a hash set or dictionary, that's typically O1 almost constant time, super fast, no matter how big the set is.
Huge difference if you're doing lots of lookups.
Game-changing difference. So pros think, what operations will I be doing most often? Searching, adding, removing, accessing by index. And then they choose the data structure, list, set, dict, heap, tree, etc., that is most efficient for those specific operations.
So don't just use the default. Consciously choose the optimal data structure for the task.
Right. Know your data structures and their performance characteristics.
Okay, 4th pro practice. They automate performance checks.
Yeah, you can't just rely on individual developers always remembering every single performance pitfall or manually running profilers all the time. It doesn't scale. So professionals try to build performance checks into their development workflow.
How does that work? Like automated tests?
That's part of it.
Yeah.
You can have performance regression tests that fail if a code change makes things significantly slower. You can use static analysis tools or linters configured with rules to flag common performance anti-patterns automatically as you type. You can set up continuous profiling in your testing or staging environments to monitor performance over time.
Tools like PySpy or the monitoring in Chrome Dev tools, or maybe those AI code analysis tools the article mentioned.
Exactly. Tools like PySpy for live profiling, JMH for Java benchmarking, even AI-assisted tools like Codant that claim to analyze code for inefficiencies. The goal is to make performance visible and catch issues early, automatically, before they cause major problems in production.
Catch problems upstream with automation. Makes sense. And the final point, number 5, they think about performance from day one.
Now, this might sound like it contradicts avoid premature optimization, but it doesn't really. It means being mindful of the common, well-known performance pitfalls like the 7 we just discussed, and making reasonably efficient choices from the very beginning, as long as it doesn't make the code significantly more complex or obscure.
So it's not about micro-optimizing obscure C code from the start, but maybe choosing a list comprehension instead of a known-to-be slower for loop with .append when you're first writing that data transformation.
Exactly that. Or thinking, okay, I'm going to need to look up items in this collection frequently. Maybe I should use a set or dict right away instead of a list. It's about avoiding known inefficiencies from the start, because lots of small, poor choices can add up to significant slowdowns later. It's building with performance awareness.
Okay, so pulling this all together, writing fast code isn't some secret magic. It's really a combination of things. First, understanding these common mistakes like logging too much, using bad loops, the N+1 database problem, ignoring hardware realities like caches and UMA, memory fragmentation, autoboxing, cache misses from array access, and accidental data copying.
Right. Knowing the pitfalls.
And then pairing that knowledge with the professional mindset and practices. Profile first, don't guess. Avoid optimizing things that aren't slow. Choose the right data structures for the job. Automate performance checks. And just generally think about efficiency reasonably from the start, avoiding known bad patterns.
It really is about becoming a more deliberate, more informed developer, understanding the why behind the performance advice.
These really do feel like lessons learned the hard way, like the author said. Hopefully, talking through them helps you, the listener, avoid some of that same frustration.
Absolutely. If you can keep those 7 mistakes in mind, logging loops, DB in loops, hardware secrets, fragmentation boxing, cache misuse, and copying, and try to adopt those 5 principles profile, avoid premature optimization, write data structures, automate checks, think ahead, it can really change the game for the code you write.
Definitely. And that leaves us with one final thought for you to mull over, something building on all this, especially that hardware section. Given how much performance can depend on the nitty-gritty specifics of the hardware and the language, what's one thing about your own typical coding environment, or maybe your favorite programming language, that you should probably investigate a bit more deeply? What might be its unique dirty secrets or hidden performance costs that you're currently taking for granted?
Yeah, what's a common pattern you use or a library feature you rely on without really knowing its performance implications? Maybe it's time to dig in a little.
Something to think about. Take some time, maybe look up some profiling guides specific to your stack, and see if you can apply some of these insights to your own projects. Happy coding!